Hey everyone, so we're looking at a topic of static equilibrium. Basically, we're looking at situations where things just aren't moving, and we can use that to solve for an unknown force. Now, when things are not moving, they're not going to move, the acceleration is going to be zero. So it actually makes these problems a little bit easier. So let's start with this question here. We have a ladder at rest, and it's leaning against a wall at an angle. Which of the following forces must have the same magnitude as the frictional force exerted on the ladder by the floor? So we're going to sketch a free body diagram. And actually, you're just going to sketch a picture first. Now, we're oversimplifying this question a little bit because we know that the ladder isn't just like a ball, if you will. This is actually like a simplified rotation question, but we do have to use some of the basics that we know now in order to solve it. So here's our ladder leaning against the wall. So let's think about the forces acting on this ladder. The first force we could draw, I'll try to keep with my color conventions. We have the wall pushing against the ladder to the right. So this is the force of the wall, we'll call it. Another force acting on the ladder is the floor pushing up on the ladder. So there's kind of two normal forces here, and that makes sense because there's two surfaces. Force of, I'll call this force floor. All right, let's think about other forces that are going on here. Another force we know we have is gravity. We will draw that from the center of mass. And if you said to yourself, well, these are the only three forces acting on it, the force of gravity and the force of the floor will cancel, but there's nothing to cancel out with the force of the wall pushing to the right on the ladder. Think about a ladder for a moment. If there's no friction between the ladder and the floor, it's simply just going to slide down, right? That's why ladders have footings that sometimes have rubber on them. So there is a frictional force that is keeping the ladder in place. It's preventing the bottom part of the ladder from sliding out to the right. So the force of friction is pointing to the left. Now we can do the whole sum of the forces here, and I'll do it just for good measure. We know that the sum of the forces in the y direction is going to be equal to 0 here. I'll skip that step because the acceleration is 0. So we know that the force of the floor pushing up on the ladder plus the negative force of gravity acting on the ladder is equal to 0. So those two things have to be equal. Now, this is a lot of work to show for a question that doesn't really need that much work, but it's always good to go back to the basics sometimes. Fx equals 0. We have the force of the wall pushing to the right plus a negative force of friction pushing to the left. So the force of the wall is equal to the force of friction. So I think the question is, which force is or must have the same magnitude as the frictional force? It has to be the force of the wall pushing against or pushing on the ladder. So it is the normal force exerted on the ladder by the wall. Notice how they identify it as the normal force, which we kind of mentioned earlier. All right, so let's see what's going on in this question. A box of mass m hangs from massless strings. We have a couple angles there, a couple tensions. Just look at the picture for a moment. If T1 is the tension in string 1, derive an expression for the magnitudes, of the horizontal and vertical components of T2. So one thing we have to figure out here is, where do we draw our free body diagram? Or specifically, of what object do we draw our free body diagram? So your initial reaction should be, well, I'm going to draw a free body diagram for the box because that's the only object that's here. I'm just going to label this as just T, just to make things easier for us. So if I were to draw a free body diagram for this box, the only other force aside from tension would be mg acting on it downward. Fg, really. So I shall fix that just so there's no confusion. So for the box, the sum of the forces equals the mass of the box times its acceleration, but it's not moving, so that's 0. There are two forces acting on the box. We have tension plus negative Fg equals 0. So the tension in the string is equal to Fg, which is really just mg. That's good to have on hand. Now we have to draw another free body diagram. But the question is, where do we draw this other free body diagram? There are no other objects. Bear with me here. I know this is going to seem strange. We're going to draw a free body diagram for this little bit right here. Okay. Now you might be saying, why are we drawing a free body diagram for that? That object has no mass. You're right, it has no mass, but it also has no acceleration. So we can use it here. Okay. And it kind of becomes, if you look at it, it's kind of like the obvious place to draw it because you can get those X and Y components pretty easily there for T1 and T2. So if I were to draw a free body diagram for that object, I would just have T1, T2, and T. So I'm going to redraw it, but as I redraw it, I'm going to put the components in. Though those should never be in a free body diagram, it's going to be really helpful here. So we have T pointing down, and then we have T1 going up into the left. We'll call that T1. And then we have T2 going up into the right. Call that T2. All right. This free body diagram might get a little bit messy. Oops, that's not where I wanted to zoom in. Sorry about that. I'm scrolling around a little bit. Okay. So these vectors need to be broken into components. I'm going to do a little bit of similar, congruent angle stuff. So if you lose me, you can ask me when we get back to school or ask a friend how I ended up doing that. But I'm going to break T2 into components really quickly. So T2 has a horizontal component. I will call it T2x. I'm going to make that dotted because as I've said before, components aren't really supposed to go on free body diagrams, but I don't want to draw a second free body diagram right now. So this is going to be T2x. One thing I want to note is that this is going to be equal to theta 2. So this is going to be T2 cosine of theta 2. The y component of T2 is going to be right here. That's going to be T2 sine theta 2. If you're wondering how did I get that angle was T2, we have, I think it's alternate interior angles might be what it's called in geometry. If that's theta 2, then theta 2 is also going to be down there. We're going to use that same idea over here. So this is going to be theta, this is going to be theta 1 will be right here. So this is going to be T1 cosine theta 1. And this is going to be T1 sine theta 1. Now, the direction of the arrows is very important because that will tell you if they're positive and negative. Positive or negative, rather. So, let's create expressions for the components of T2. All right. So, what we know here is in the x direction, we'll do that first because that looks a little easier. The sum of the forces in the x direction are equal to 0 because nothing's moving here. We have two forces in the x direction. We have T2 cosine theta 2 plus negative T1 cosine theta 1. That's equal to 0. So we know that we're looking for an expression for the horizontal component of T2. Actually, I didn't even read the question that well. We can actually make this a little bit easier. I'm just going to call this T2x because I don't even have to do any work. I just have to call this T2x. That actually make it a little bit easier for us. And that kind of makes sense because we'll call this T2y. That makes sense because AP physics questions generally you should be able to answer them in about 2 minutes if you really know what you're doing. So it makes sense that they actually made it a little easier for us. We're just looking for the components. My natural reaction was to call it T2 cosine theta and T2 sine theta. I don't even need to do that. So let me touch this up a little bit. So I'm just looking for the T2x. So T2x is equal to T1 cosine theta 1. All right. Again, I'm just looking for the horizontal component of T2. Can I call it T2 cosine theta 2? Yes. But I don't need to do that because I just need what is the magnitude of it. All right. Now let's go in the y direction. So in the y direction, I have the sum of the forces in the y direction are equal to 0. So I have three forces in the y direction. I have T1 sine theta 1, that's positive, plus T2y, which is positive, plus negative T equals 0. One thing you have to recognize, though, is that capital T was not given to us in the question. I made it up. I need to remember that T is equal to mg. So I'm just going to kind of bring that in here. So I'm going to make one big step right now. So try to do this step on your own. T2y is equal to mg minus T1 sine theta 1. And that would be our answer. This was a multiple choice question. So one thing about the multiple choice questions is that sometimes once you get one of them, you actually don't even need to find what the other one was. You can use process of elimination. All right, let's go on to the next one. I'm just checking my work here real quick. Yep, we're all good there. All right, so this is actually quite similar to the previous one. So I'm just going to zoom out a little bit. All right, so just look at what's going on here. So horizontal wire shown at the right and the figure above will break when the tension in it exceeds the value T max. What is the maximum mass that the hanging object can have without the horizontal wire breaking? All right, so we're defining T as T max. Assume the wire on the left does not break prior to the horizontal one breaking, of course. Okay, so let's look at this real quick. All right, so this looks good to me. I'm just gonna think about where I wanna draw my free body diagram. I'm gonna kind of sketch this in right here. Okay. Hopefully you recognize right now that the tension in this string right here, the tension right there is going to be mg for the same reason it was in the previous one. I'm not going to go through that again. The reason I don't want to define that as T is because we already have a T defined. I don't want it to be too confusing. I am going to call this tension, or excuse me, this one right here, let's call this T1. Okay. All right, so working from there, same process. Let's go some of the forces in the y first. I mean, I know we're looking for something in the x, but something tells me we're going to have to figure out the y direction first, or we're going to have to find it out anyway, so let's do that. So the sum of the forces in the y direction are equal to 0. Again, we're using this center point as our for our free body diagram. So let's break vectors into components. I'm actually going to draw right on this picture. So this is going to be T1 sine theta. And this is going to be T1 cosine theta. All right. So in the y direction, we have three forces, or excuse me, we have two forces. We have T1 sine theta 1, or sorry, sine theta rather, minus mg equals 0. I'll leave that right now. I don't know how much I can do with that. Let's go in the x direction, because I don't really know what I'm going to end up solving for. But if you notice, we don't have any m's in our as our answer choices. So something tells me we're not going to have m in our answer. So the forces in the x has to equal 0 also. For this one, the only forces in the x direction are T, specifically T max, plus negative T1 cosine theta equals 0. So T max equals T1 cosine theta. Okay, so now we're solving for the maximum mass. Oh, of course, we're solving for the mass. We're not solving for attention. So let's isolate m in the left-hand equation. So it's important to know what you're actually solving for. So we have t1 sine theta over g equals our mass. Now you'll notice my answer needs to have t max in it. Well, that's from the x direction, excuse me. So notice how my answer doesn't have t1. So what I'm going to do is I'm going to solve for t1 in my right-hand equation. So I'm going to have t max over cosine theta equals t1. And I'm going to plug this in for t1 over here. Okay, so this might get a little bit messy, but take your time doing it. Try to do it on your own. Try not to follow me. We have t max over cosine theta times sine theta over little g equals m. So this comes out to be t max times tangent theta over little g equals m. All right, and the last one here. A uniform spool is suspended from a vertical wall by a string. The axle, okay, the wall is smooth. There's no friction between the spool and the wall. The tension in the string is 2.6 newtons. What is the weight of this spool? All right, let's get going with the free body diagram. We have our weight pulling it down. That is our unknown. We want Fg. That's our unknown. The tension in the string going up and to the left, it gives us that value. So I'm just going to put that value in right away. That's 2.6 newtons. And again, this isn't moving, so all the forces have to cancel out. Again, there's no friction. Friction will be pointing up or down here. But remember, the wall is pushing on this thing. So the wall is pushing it this way. We'll call this F wall. All right, right away, your first reaction should be, I need to break this up into components. So right now I have a horizontal component and a vertical component. Now you're not given an angle here, but you can figure it out. Think about how you can find this little angle in here. You have some dimensions in there, right? So I could probably use, let's see, I can use my adjacent side and my hypotenuse there. All right, so let's see if I could do that here. So I don't have my scientific calculator on me, so actually, oh no, I can do it. Let's see. So I'm going to do 5 divided by 13, and I'm going to do the inverse, because that was adjacent over hypotenuse, I'm going to do the inverse cosine. Okay, my calculator, my phone calculator, I'm not so good with it, is telling me that this is 67.4 degrees. So I hope that's right. Okay, so theta equals 67.4 degrees. Just give me a second to check that because I don't always trust the way I do stuff on a calculator. So 67. Just give me 3.38. All right, I think we're good there. Okay, 67.4 degrees. So I'm actually going to find the components then right away by doing sine and cosine. So to get the horizontal component right here, I'm just going to draw arrows in. I should have drawn this bigger. This is going to be 2.6 cosine of 67.4. This is going to be 2.6 sine of 67.4. All right, so Getting like 1 exactly for that one, which is kind of strange, but I guess this is 1 Newton. Let's see what the other component comes out to be. $2.4. I'm going to do that below. Actually, now that I'm looking at it, that makes a lot of sense. If you look at the triangle, you can see how it's 5, 12, 13, 26, and 13. So you kind of double it. So you get 24 and you would get 10. So that actually makes perfect sense. All right. So let's find the weight. So the weight is in the y direction. Let's see if we can get it without bothering with the x direction. So the sum of the forces in the y direction are equal to 0 because nothing's accelerating, right? So in the y direction, I have 2.4 newtons upward plus a negative force of gravity, and I have no other forces in the y direction. So 2.4 newtons is equal to my force of gravity. That's it. I don't even have to do the x direction. So again, you should always be thinking to yourself, how am I going to modify these questions on a test? Well, that's a great way to do it. I could just ask you the same question, but instead of asking you for the weight, I can ask you for what is the normal force acting on the spool.